Okay, hopefully that started recording. Yes, it did. Okay, greetings, folks. Welcome to Physics 10, Tuesday, Thursdays, 9:30 to 10:50. I am standing in our classroom, so and it's empty. So this is a new one for me. Hi, my name's Marcus. I'm going to be the person you see for the next 15 weeks or so, and we're going to be talking about physics. So hopefully you enjoy this. I mostly concentrate on trying to talk through and think through the ideas of physics. And this is something we'll get into a little bit more on later. And the homework is generally questions and answers rather than mathematically based. So hopefully that's going to be something you're looking for. We are pretty low on mathematical requirements. I'm not gonna ask too much in the way of that. It's mostly going to be thinking about the concepts and trying to think about how to take the concepts and apply them to different types of situations. So a couple of administrative class things before we get going. And I did just kind of talk through this a little bit with folks just before the recording. So let me go and do that again. If there's a problem at any point with either my audio or video or what you're seeing on the board here, we kind of talked through it, and it looks like this is the best size font. Approximately in black is kind of what I'm going to be going with. I'm going to be trying to write larger, whereas that's a little bit too small. So I'm going to be trying to write bigger, which means I'm going to be doing erasing and stuff like that. So since we are recording, you do have the option to go back and look at this later. So that's good news. If at any point you can't read and there's problems, or there's problems with my video, or there's problems with my audio, please put your microphone on and yell something at me, because I can't really monitor the chats. And the reason is because, like I told you, I'm in the classroom, and my phone is the thing that I'm doing this on. And, you know, it turns out that your eyesight gets worse as you get older. And I found that out. I went to have my eyes checked the other day, and I don't see so well. So at some point I'm getting new glasses, hopefully this week. I don't know, maybe it's next week. So I can't really, if you have a question, maybe the thing to do, I don't know, maybe type it in the chat so that I can go back later and look at it, because I get a transcript of that too. But definitely use your microphones. I want this to be a thing where I don't mind being interrupted. So if you have a question, just start talking, because I'm not sure that I can, like if you do one of those hand waves or things, I'm not sure I'm going to be able to see it. That's my only problem. So if you just say, hey, then I'll stop and we can have a conversation. So hopefully that's okay with everybody. If you have better suggestions, I would say leave them in the chat, or maybe you can send me an email. So yeah, if at any point I slip and I start going back to the small writing, yeah, just, hey, stop, I can't read what you're writing, make it bigger. Okay, that's fine with me. I don't stand too much on pretense. Okay, a couple of things, more administrative stuff before we get going. Okay, so yeah, any questions at any time, just interrupt me. The Canvas page should be up and running. I hope it is, and I hope that most of you got an email from me. If you are on the video, but you didn't get an email from me, and you're here because you were on the Canvas page, If you did not get an email from me, please send me an email saying I didn't get your first email. That way I can check the enrollment and the status of everybody. So that's good. On the Canvas page, I've tried to go simpler. In the past, let's see, I have taught this class online once or twice before, but in the past, I've put up multiple things, and I'm changing that. So I'm going to have every week, there's going to be one page for each class, and we're Tuesday, Thursday, so we're not going to miss anything until spring break. So every week there'll be a class link to the recording. So there's 2 of those every week, and then there'll be a homework page, and then there'll be a quiz page. And I think that's going to be it. On the class pages, I'm going to put any links to videos that I'm going to use. We're going to watch one today, which is linked off the Canvas page. So in the description for today's class, there's already a couple of things that have been linked in, a couple of videos. And so you can, if for some reason it doesn't show up, because I'm going to be ridiculous, and I'm actually going to move my phone over to look at the screen that I'm projecting in this room. And if that doesn't work, then I'm going to have to try and figure out how to share my screen and get on Canvas on my phone and do all of this stuff. I'd rather just try to keep it this way. If this doesn't work out, look, we'll make adjustments. That's not a problem. So what else? That's pretty much it in terms of what you're going to see on Canvas. The homework due dates should be listed out. The first one's due next Thursday. Yeah, next Thursday. It should be the 9th. There will be a quiz on the homework stuff on the same day that the homework's due. All right. So here's how I want to do the homework and quiz stuff. And the celebration stuff, which is my code word for exam. I call them celebrations. And now we all do. So the homework I'd like uploaded into Canvas. So on next Thursday, when the homework's due on the 9th, you have until, midnight, 1 minute to midnight on that day to load the homework in. Screenshots, scans, photos with your phone. I think that's all going to work just fine for me as long as I can read it. So make sure you submit those. Now the quiz is going to be enabled that same day for the whole day. So it'll become active right around midnight and shut off right around midnight. Okay. So you'll have about a 24-hour period right there to do the quiz. What do I want to say about that? Well, in general, there's some multiple choice questions that are going to be asked on the quiz. There are some on the homework, but I'd like the homework, but I mean, it's not where you can just enter in an answer. You have to actually write out stuff and then submit it by Canvas for the homework. For the quiz, there's going to be questions on the screen that you can click answers to and then type an answer into, and then it should submit that way. And there's I can't remember, I think it's a 40-minute time limit or a 45-minute time limit. I'm gonna have to remember that. But some of the quizzes may be something where you need to write something down on paper. If that's the case, then the quiz time, I'm gonna allow 5 minutes at the end of the quiz for you to take a picture and upload that document. Okay, so when there's quizzes like that, think about subtracting 5 minutes, making that your quiz time, and then the last 5 minutes is for submitting it, okay? It's not the whole thing for working on the quiz, because then it's going to shut you out and then you can't submit the quiz. All right. So when this kind of thing occurs, just try to think about taking 5 minutes less and doing the whole thing. So I would normally be giving 20 minutes for the quiz if we were in class. So I'm giving you double that, and that should be okay. Hopefully, fingers crossed. Again, we're rolling along here, and if we don't get something right, please let me know as soon as you can. I am pretty amenable to changing stuff on the fly, and trying to see what's going to work best for you all. All right. At this point, I'll throw it out. Any questions that you want to ask, which I could answer?
I just want to mention, can you hear me? You mentioned that it was February 9th. It looks like the homework and the quiz are both labeled on Canvas as February 7th. So that would be next Tuesday, not Thursday.
Okay, my bad.
No worries. And it looks like you did give us 45 minutes for the quiz. So.
Okay, thank you for checking on that.
No problem.
Okay, that's good. I mean, I must be mixed up already. So first homework is next week. Let's see. All right. Here's what I would say. If so I'm also doing this on a schedule in which I approximated what I would have done normally during the semester. So if we run slightly back for whatever reason, or if we have technical issues, or if we're just running a little bit back, then dates will get adjusted. I want to emphasize I'm flexible with stuff that is going to be of use, especially for your learning purposes, especially in a format like this. Okay. All right, so homework's next Tuesday, so that's good. Maybe we should get going on some stuff. And I can tell you how to answer some of your homework questions. All right, video homework quiz, celebration. All right, I think we're ready to go.
Actually, can I ask one question?
Yeah, go for it.
I was about the book, and if it says recommended, like, do you want to talk about that?
Yeah, the recommended text is Hewitt, and I only recommend it. I don't require it, in other words. All the homeworks will be written out. I'm not going to refer to problems out of a textbook, so I'm not going to use a textbook to give you homework. What the textbook would do for you is give you a little bit more reading to do on a particular subject. So I recommend it if you like one. Some people, would prefer to read. Great. Then Hewitt's textbook, I don't think you can really even get your hands on any edition lower than the 10th at this point. Maybe you can get the 9th, but I think it's up to edition 13. Look, my point is that I don't need you going out spending $250 on a textbook. We're really not going to make a lot of use of it as a required thing. Well, we're not going to make any use of it as a required object for this class. You might want to make use of it as a supplemental tool. If that's the case, I would definitely recommend getting one that's 20 or 30 bucks rather than 250. But you probably don't need me to tell you that. So look for the lower editions, 10, 11, 12, maybe 9. They're all pretty much the same in terms of what's in them. All right, so hopefully that answers your question.
Thanks.
Okay, so what I'd like to do is let's have our first video experience. We'll see if this works. This is hilarious because It's a class on Zoom in which I'm using it in a completely ridiculously old way. But anyways, let's try it and see if it works. And if it doesn't work, then I will figure out different things to do. So let me walk around. Oh, I'm gonna say this also before I do that. You are on my phone, sitting on a tripod near the front of the classroom here. I am gonna move you around so you can see stuff. The reason I chose to do this in the classroom was because so I can bring in things that we have and I can show you and do demos for you. And that's going to mean I have to push you back a little bit so you can see the whole thing in front of me and move around. So I will be walking around, moving you from different places to different places in the classroom. Hopefully that works out. Let's give it a try. Okay, here we go. We're going to go over here. And I'm going to see if we can't angle this up a little bit. I'm going to put it right about there. Let's see if we can angle this up a bit. All righty. Okay, now how does that look? Can you read those words?
Yeah.
Okay. Let me try the sound, because the sound is going to be coming out of the speakers. And there's a lot of people walking past the window wondering who I'm talking to in here. Okay, let's do this. Oh, I got another thing to do. Let's dim the light. Okay. All right, let's give this a try. Okay. Can you hear and see this? Is this good?
It's really low quality audio.
I can see it, but yeah, the audio is kind of wonky.
Okay.
It's like just super like compressed.
The let me try a little more. As you notice, it's from the 70s. So that was 70s intro music. Let's see if you can hear the voice.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October.
Okay. Any better? No? Yes?
It's okay. I can't help but say I would rather just like have the URL and go watch it in
Yeah, you
quality
can.
on my own.
It's in the Canvas page. This is the first one.
Is it possible that the closed captions work on the video?
Probably.
That's easier to see.
All right. Let's see if I can get you forwards a little bit more here. Okay. Let's go this way. All right. Okay. And again, like I said, if this doesn't come through, no big deal. It is linked through the Canvas page. It's the first one. And it's only about 9 minutes or so. So we're going to take probably not the whole time to do that right now, but let's take a look at this and see what we got here.
We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. we see the great city on the lake shore. 10 to the fourth meters, 10 kilometers, the distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake, 10 to the fifth meters, the distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the sixth, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun. Followed by the massive outer planets, swinging wide in their big orbits. That outer orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. Next will be 100. Our perspective changes so much in each step now that even the background stars appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a scaled version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of a sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds. Each step much smaller than one before. At 10 to the -2, 1/100th of a meter, 1 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of a powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion, swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in the tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our seat, we reach the edge of present understanding. Are these some quarks of intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
All right. So that was a video, like I said, from the 1970s. Oh yeah, you can see here, 1977. You know that it's something that is a kind of it's a relic of society. Like you really made it when you get mocked by the Simpsons. So let's do this. Wow. All right. Well, there you go. You know it's an icon when The Simpsons is going to do something for you. All righty. I'm going to move you back to the front here. Let's put you up here. All right. I'm going to turn the lights back on and we will get going. Okay. All right. Let's see here. Let me tilt this back. All right. How's everybody doing this morning? Nice little video break. Whoops. All right. How about there? No, I'm not there. Okay. Okay. Good stuff. So those two videos are linked up on the Canvas page. They are the reason I like the first one is because it really shows the extent to which we as physicists try to understand things. Now, what really, we might as well ask, what really is physics here? And not only that, how is it
Sorry,
related?
is anyone else getting like feedback sounds? Or is that just me?
Yeah, I am too.
I am too. It's like a ringing.
I am as well. Yeah.
That any better?
Seems like it's stopped.
Okay. If it comes up again, just let me know. I think it might have been the speakers from the videos in the classroom here. So hopefully, yeah, hopefully it's gone. If it comes back, let me know. Sorry about that. All right, so thinking about physics in relation to the other sciences. We have other, we have kind of one big overriding question that we want to ask, which is, why are we here? And maybe that sounds like a pretty big question, but branches of science exist to try and answer and provide information to that question. So we have lots of other sciences. We have geology. Okay, we have physics, we have chemistry, we have biology, we have geology. These are all sciences which are kind of trying to figure out something about why we're here, what's around us, what makes us who we are, how did we get to be here, what's around us, and how did that get to be here? So these are questions that we try to answer, and ultimately, you can think about what each of these fields is kind of studying. Geology, of course, is about rocks and Earth particularly, but also rocks and the materials of other planets. Biology is the study of life and what it means to be alive, and how do things become alive? How do you reproduce and have children that become alive? And how do trees and plants and animals, how do they exist, and what makes them what they are and not what we are? Okay, so biology kind of touched on a little bit in that video with the skin, the lymphocytes, the DNA, the stuff like that. Chemistry, mostly the study of what materials exist, what makes things up. One of the big things for chemistry, if you've ever had a chemistry class, is the periodic table of elements. And that's essentially the ingredients of the universe. We've discovered essentially what everything is actually made out of, and chemists are mostly interested in trying to figure out what the properties of these things are. And physics is something that is most fundamental as a science. It's the one that asks, okay, if you're a chemist and you're interested in why a particular reaction happens, you'd say, well, it's maybe because electrons transferred, or maybe it's because, right, you take, I don't know if you've seen any typical chemistry experiments, like you take two clear liquids and you pour them together and they turn blue, or something like this. Or if you've seen the, gosh, what's it called? The elephant's toothpaste. Or I think Mark Rober has a video on this, like the devil's toothpaste. So he just made it very much bigger. So why does that chemical reaction happen? Why does baking soda and vinegar? Why does Mentos and Diet Coke happen, right? Why does this stuff happen? Well, that's kind of a good physics question, because we're people who dissect the elements and we look at what's an atom. What are atoms made of? Why do atoms react the way they do? What makes them different from other atoms? So that's really a physics question. Also, on the other hand, on the other side of things, when you got to the big scale in that video, we were looking at clusters of stars, clusters of galaxies, right? Planets, what comets, how are those existing? What are they doing? What kind of motion do they have? Again, these are questions that physics has investigated and tried to provide an answer to. So ultimately, there are lots of different branches of science. We're all trying to kind of get at the same thing. So for me, one of the things I really like about physics is that because we are looking for the general rules of things, like for example, if you could say, well, what's made of stuff? I would tell you that atoms make things, right? Everything's made of atoms except for things like light, right? I would say, okay, what's this made out of? Oh, it's made out of atoms. That's a general rule. That's basically generally true for everything, no matter what you look at, whether it be skin and cells or concrete or plants or whatever. When you get right down to it, they're all made of atoms. So that's a general statement. That's a physics statement, right? A chemist would say, well, this is made of particular this and that and the other, and this is made of something else altogether completely different. But for us, it's all just made of atoms. So physics is the most general science, and I appreciate that because it means there's a lot less to remember. We're trying to look for the big general rules that we can apply to everything. So if we know those rules, we can look at 150 million different situations, but I've only got a certain number of rules. I don't have 150 million different rules. I've got 5, and I'm going to apply them to all these different situations. So that's what we end up doing. So the physics laws are the things that we really want to spend time looking at. All right, so that being said, I do want to talk a little bit about science in general. And I want to talk about science and what science tries to do. Well, I guess, you may have heard that a few years ago there was kind of a large outbreak of disease worldwide. And I have a few friends, and they had theories about how this disease came to be, and what what it was and what it was transmitted and all that stuff. So I want to address the idea of trying to take a question and answer it scientifically. Because I, of course, being who I am, had to kind of address this with my friends and say, well, wait a minute, so if that was true, then that would mean that, these people were acting by themselves, or, COVID was brought to us by aliens who dropped it off in spaceships so that they were invisible and we couldn't see them. Right? They came up with these ideas, and you have to say, well, wait a minute, how does this work? And one thing that I kind of kept running up to is, well, I believe that it's this way. And I kind of got to thinking about that, and I realized that once someone says, I believe something, then that question has been taken away from science for that person. For example, there's people believing that Earth is flat. And that's what I mean. They believe that. I can try and present evidence to the contrary, but it's not going to do any good. You follow me? They believe this. This is now part of their belief system. So I want to kind of just address the idea of science versus belief. And if there's a question and you believe an answer to it, that question is no longer part of science, right? Whereas what science tries to do is come up with an idea as to why the answer might be one way or another and try to explain what's going on the best we can. And then what we do, this is a super important part too, we talk to other scientists and say, well, what do you think? I think maybe it could be something like this. And they'll say, oh, that doesn't sound bad, but this isn't really the way I would have done it. I would have done it this other way. And so peer interaction and feedback is a huge part of doing science. That's how physics gets laws. Some of the laws we're going to talk about, say next week, were established, were first thought of about 250 years ago. And through the time from 250 years ago to now, they seem to have passed a lot of tests. And we seem to think that they're pretty useful. And that's why they keep going on. Ultimately, what determines whether a science idea like an explanation is good? What determines whether the explanation is good? It's whether it passes tests. You have to test it. Okay, so you might think of, oh yeah, I think I don't know. I think that what, this table will crack if I throw this tennis ball on it. Oh, it didn't. I was wrong. Okay, and so that's part of science, being wrong a lot. So anyway, so a little bit on science and what we're trying to do there. Let's start a little bit with some of what we know about our local environment, which is to say what's going on with Earth, solar system, stuff like that. Okay, so you probably already know some of this, and that's great. I kind of want to consider this knowledge that everyone should have. So I'll do my best here. Let's see. I'm gonna have a. All right, like something like this, where I've got the sun here. By the way, this is not drawn to scale, as the sun is huge and it's really far away. So the sun's here, Earth here, and moon right next to it. Okay, so there's Earth and the moon. And I said I was going to write bigger and I didn't. There we go. Okay. All right. Hopefully that's a little better. It was thought for a long period of time, approximately 1,500 years, that Earth was stationary. And the sun moves around Earth and moon moves around Earth, and the stars, which are way out there, kind of rotate on this big thing that rotates around us somehow. And we know now that that's not true. You probably, I mean, my daughter learned, my kids, I have a son who's 12 and a daughter who's 9, going to be 10 soon. But I remember them learning when they were, 4 or 5. Oh, there's a solar system and there's different planets and they all go around the sun. Okay. Well, good. The question is, how do we know? How do you know that that's what's happening? Because we've all learned it. But how did we get to knowing that this was the case? And it literally took almost 2,000 years for people to figure this out. So it's not something that you can do overnight. Okay. It really is something that is not a straightforward thing. And I could challenge you to go out tonight or even, whenever during the day and say, prove to me that Earth goes around the sun. And you wouldn't be able to do it. Because everything you see, right, during the day, what does the sun do? Meow. Right? What does the moon do? Meow. What do the stars do? Meow. It looks like we sit here and everything goes around. So how did we figure this out? What's the situation? It's something that it would take several months to really deduce. If you were to go out and look every night, you could do this, but you can't do it in one day. This is a really deep piece of knowledge. How did we know this? We know this because there are other planets, okay? And these other planets move around in the sky too, but they don't do it in a way that just goes meow. Sometimes they go meow, meow, like that. And by the way, the sound effects are super important for that, just to let you know. If you look at every night, you go out and you look at this at say Mars, okay? You're going to watch Mars every night. You do it for a month or two, and you find Mars doesn't just move in the same pattern as the sun and the moon do. Mars moves a little bit this way, and then all of a sudden moves back this way, and then moves this way again. And just from that tiny little observation, we can actually deduce that it's us on Earth that's moving around the sun. And let me tell you why. Okay, so Mars that's a little close to the edge. Let's see there. Okay. So Mars okay. Mars goes around the sun just like we do. But it's a little further away. So it's a point of view perspective that causes Mars to have a loop in it. From our perspective, it doesn't have a loop in it if you look at it from the sun. Okay. So here comes Earth and here comes Mars, like this. And you look and you say, okay, in general, if we're further away from the sun, the time it takes us to go around the sun, what's your feeling about this? Is it going to be quicker if I'm further away from the sun? Or is it going to be a lot longer if I'm further away from the sun?
Longer. Longer.
It's going to be longer. If you know, for example, a Jupiter year is 14 Earth years or something like that, meaning a year, meaning time around the sun. So if I look at this, Mars is moving less quickly than Earth is. So we actually pass by. If you look at it and you say, well, I'm going to consider Earth here, and I'm going to see Mars over there, right? And as we pass, right, here's Earth here, and we're looking at Mars, and it's moved a little bit. I'm cheating a little bit with not moving Mars. But if we look at it, right, by the time Earth gets over here, we're looking backwards at Mars. So the direction of Mars, from our point of view, seems to have changed. It was that way, and now it's going this way. And as you go quicker in the inner cycle, in the inner orbits, you pass by these outer planets, and they make these little loops in the sky. And so to describe that, people said, oh, what if we all just go around in circles? And then all of a sudden, that's kind of how it came to be. And of course, in much later years, we can do things like launch satellites to look around, and sure enough, this is what we see. So just even knowing something as simple as Earth goes around the sun, that took a heck of a long time to figure out, and a lot of careful reasoning and a lot of data taking. It's really an amazing piece of knowledge. So enjoy that. I want to talk to you a little bit also. How do you know when you're looking at a planet versus looking at a star? Anybody know?
Stars have like luminance. And they're at the center of like a solar system.
Center of a solar system, how do you mean?
Well, I mean, like, they're usually the most massive things in like their system, so they're usually the center because they attract all the other planets around it.
True. So sometimes what we can do is we can see planets going in front of stars, and that's how we would know. So what you look at the stars, the amount of light it's putting out, and then if something goes between it and us, we see it kind of diminish a little bit because it's kind of shadowing us. It's blocking the light to us a little bit. So it looks like it gets a little dimmer, and then it gets brighter again, and we go, oh, maybe there's a planet there. Yeah, so if you looked at that, there is a way to look at with just your eyes, though, and see. I can tell the difference between a planet and a star. Any ideas? There's that. I totally agree with that. That's a good way to do it. There's a slightly easier way. Stars twinkle. Planets don't twinkle. Ain't no twinkling on the planets. You look at the planet and it's just, it's usually a little bit brighter and a little bit bigger than stars. But if you look at it, it doesn't do that thing where you can see, right? And if you look at a star, it's usually doing this. You look at a planet, it just does this. So a planet doesn't actually have that shimmery effect that the stars do. Check it out tonight. It's been clear for the last couple of nights. I can't remember when moonset is, but look somewhere away from the moon because moon's too bright to be able to see this. You go find a planet, you'll see them though. I think actually Venus is pretty close to the moon right now. But anyways, from our perspective. So you take a look at Venus, for example, and you say, Venus is a pretty interesting cat. Okay, take a look at Venus. Venus is going to come up here. And it's going to sit right up here. I'm going to get rid of some of this. Okay, so suppose this is still us on Earth. Okay, I'm going to draw Venus. In 4 positions. Take a look at Venus. What does Venus look like to us? What's happening to Venus right now? If we're sitting on Earth and we look at Venus right now, what do we see? What does Venus look like to us? Is it really light? Is it dark? Is it half light, dark? Is it just doing whatever? What do you think?
I mean, doesn't it like reflect the light from the sun?
It does, but where's the sun? So the sunlight hitting here.
It's going to be dark. It's because it's eclipsing it.
Yeah, it's going to be dark. So this is a phase of Venus. What does Venus look like up here?
Half.
Yeah, so right? The sun's going to illuminate this side of it. This side's going to be dark. We're over there, and we're looking at it this way. So we see half light, half dark Venus. What do we see over there? Remember, this picture's not to scale.
If we could see it from the gravitational pull of the sun, it would be fully illuminated.
Exactly. We got to kind of see around the sun. That's what I mean. Sorry about that. Yeah, totally, right? The dark, oops, where's my black? Here it is. The black is there. That's the night side of Venus. If we're on Earth looking past the sun, Venus is going to be full, right? And it's going to be back to half here. Venus exhibits phases, just like Moon does, right? Have you all just a couple of nights ago, the moon was beautiful. It was a crescent. It was just setting just after the sun went down. It's great. Love watching the moon when it does that. A little while ago, it was half, maybe about half now. Venus does the same thing. And that's another reason we know that Venus is an inner planet, because it undergoes phases. Now, examine what happens if it's an outer planet, right? If we are looking at Mars, for example, here's Mars. Right, might be on the edge of your vision there. Can you see that? Yep, okay. So here's Mars. If Mars is here and we're on Earth just in front of it, what phase do we see Mars?
Pretty much full.
It's got to be full, exactly. Now, if Mars goes around here and it's far out, I got to redraw the picture. Sorry, I got to redraw this. Yeah. Okay. Let's take Earth and Mars out of here. Okay. Now, suppose this is Mars orbit right here. This is Mars. I'm going to make this Mars. Okay, we are in here. Here we are. This is Earth. This is us right here. We're about to get burned to a crisp. Okay, check it out though. Okay. So there's where Mars, that's the one we just did. If we're on Earth and we look at Mars that way, Mars is full. If we're here and we look at Mars, Mars is still full. Still full, no phases. Mars is further away than we are. This is how you can deduce the relative placements of the planets. All right, so we're doing pretty well. We figured out that we go around the sun despite everything that you see. Think about that, right? I still love that. That's an amazing fact. And if you think about how you would figure that out, it's not simple. Oh, well, it's kind of simple, but it takes a really long time because you got to observe the planets. All right, and we've just ordered the planets, right? We know that the inner ones are going to make phases, the outer ones are not. Okay, so we know about where we are and we know who our neighbors are. Good times. Okay, questions so far? Anything that you'd like to see or hear about?
So, using that, you can tell that some planets are closer to the sun than we are, and some planets are farther away. But how do you tell, for example, the order? Like, how would you tell that Neptune is farther away than Mars?
That's a great question. And it comes down to the idea that if you're further away, you're going to move slower. So if you chart the positions of the planets, the ones that are moving, you know, night to night to night, you look at over lots of time, right? You go observe the planets for, you know, a couple of months and you watch them. The ones that are further away don't change their positions as much as the ones that are closer, right? Sometimes you'll see Venus and it'll be over there. And sometimes you'll see Venus and it'll be over there. Venus moves pretty quickly, right? It's either the evening star or the morning star. It's not a star, it's a planet. Never mind that. But it moves around pretty well, pretty quickly. And then you look at Jupiter and Saturn and they're going to be like, oh, they're right there. And then you go out the next night and they're still right there. And you go out like a month later, they're still about right there. So it comes down to their relative motions as we observe it. Yeah, excellent question. Other questions that we want to go over? Okay. All right. So the moon does something similar to this, right? Moon orbits Earth, and we get things like eclipses and things like that. So let's narrow our viewpoint a little bit. Instead of looking big, the sun and the planets like this, I'm going to put the sun over to one side. And we're going to take a look at what Earth and Moon do together. The dance of Earth and Moon. Okay. All right. Hey, it's an online class, buddy. Get out of here. Okay, sorry. One of the other instructors is making faces at me behind the door. All right, I'm going to put the sun right there. Can you see that? So here's Earth right about here. Sorry. Oh, man. So here's Earth right about here. We are dark on this side because sun's on that side. So this is Earth here. And let's say Moon. Let's draw the phases of Moon here. Let's put Moon right about here. Okay, 1, 2, 3, and 4, like that. So let's assume that everything is stationary for a second, and we can just rotate the moon around us as we would like. Okay. So if we draw in the phases of Moon, I would draw them just like I drew the phases of Venus. That side is in shadow because the sun is over here to the left. Okay. Let's see. How's that drawing? Is that okay? Can you see that? All right. Hopefully. So we see moon phases just like we see Venus phases, right? It's just that moon's a little bit more up in our face about it, okay? Because moon is really only 250,000 miles away, which is like nothing. Venus is like way far away compared to that. So here we stand on Earth. We see full moon that way, half moon this way and this way, and new moon, dark moon, right, this way. So a few nights ago, moon was half. Now check this out. Is it surprising that when the moon is half, that the angle between moon and sun, angle between moon and sun is about 90 degrees, right? In other words, it's a corner angle, right? Check this out. If I'm standing here on Earth and I can see the moon, then I'm going to be able to look at the moon here that way, and the sun is that way. It's a 90-degree angle. So every time the sun is setting, the half moon should be either overhead or is on that side of Earth. It's already set, right? Every time sun is at local noon, moon should be either just rising or just setting, and that would be the half moon. So you can walk around like with your arms like this and say, aha, I know where moon and sun is. Look, they make 90-degree angles to each other. You should try this. It's great. You can just make about a 90-degree angle and say, there's moon, there's sun. Look at that. It's a half moon. It's 90 degrees. You do get funny looks out in public if you do this. Maybe try it in your backyard first before doing it in public. It's just to let you know. All right. So you can see now where eclipses are going to happen, yeah? Now the moon, one thing that I cannot draw here is that the moon, this plane, I've put them all in the same plane here, but in fact the moon, if I were to take it and tilt the whole thing this way, the moon's plane is tilted a little bit. Okay, because you look at this diagram and you say, how come we don't get an eclipse every single time the moon goes once around? It should, according to this diagram, but it doesn't, right? It's because the moon's plane is tilted a little bit. So when the moon goes around, it kind of goes up and down, and that plane shifts near, and every now and again, it goes right in the middle, and it sticks us with an eclipse. That's why an eclipse doesn't happen every month. It happens only once every year or two, or something like that, okay? Nonetheless, if we were perfectly lined up for an eclipse, this would be the point of the solar eclipse. This would be the solar eclipse right here. right? That's the position of moon if we on Earth are getting the sun eclipsed, right? Now, if we on Earth are getting moon eclipsed, that's this way. In other words, moon's going into shadow. It's going into the shadow of Earth. We'll talk a little bit more about that next time. But this one over here is lunar eclipse. Okay. And that's where the moon would have to be to do those types of things. Okay. So this is just fun stuff that you can just go out and look at and appreciate. I love to do, I've been looking at the stars since I was a kid. It's nice to know how and why. Okay, now we take the Earth here. I bet you didn't know I had Earth in my hands. Oh, I think I just killed a bunch of people. Sorry. So look, Earth is tilted. Something else you probably already knew. So it's tilted about 20, a little over 20 degrees, about 22, 23 degrees away from the plane of its orbit. Okay, so in other words, if I have the sun, say the sun is, well, this is, I don't have a bigger globe. I don't have a big sun. Okay, if the sun's over here off to the, well, this is my right. It's over here. Okay, and we're orbiting, right? We're spinning on our axis like this, and we go around, going around like this. Okay, but notice that the tilt is always kind of this way, right? Right now in winter, it's pretty cold. And guess what? Earth is actually closest to the sun right now. This is not a happy thing for people to hear, because why shouldn't we be warmer if we're closer to the sun? We are right at the aphelion right now. There's the perihelion and the aphelion. I can never remember which is which, but I think it's the aphelion that's the closest, or maybe it's the perihelion. Whatever it is, we're close to the sun right now. We're closer than we ever are going to be, because Earth's orbit is not circular around sun. It's slightly elliptical, like an oval. Okay, so we're actually really close to the sun right now. And then later on, when it's summer, we're going to be like way over here. Whoops, like that, right? Yeah, it's gonna be way over here. And then we get on here, and we're really close to the sun. I'm exaggerating a whole bunch right now, but okay, that's the idea. Question is, why is it winter if we're so close to the sun? Has to do with the tilt. Yeah? Has to do with the tilt. Sun, suppose sun's way over here, okay? Now, let's see if I can do this and then have you go down a little bit so you can see the globe a little better. Okay, good. So the sun, suppose, is way over here this time, okay? If I look at the light, how is the light hitting Earth? If the sun's over here and we're bathing this side of Earth in light, well, there's part of the light is hitting Earth almost straight on, right? And that's still, I want you to go down a little bit more, maybe like that. Okay, see, right? So I want to look at the light that's hitting Earth. It's going to hit almost straight on, right here. It's hitting, right? It's hitting Australia really well. There's Australia right there, New Guinea right here. We are up here, but look, is the light hitting us straight? Not really. It's kind of glancing, right? It's like if I wanted to really heat something up, I would do that and hold it right there. But right now, the sun's like way over here and the light's coming this way, and it's spreading out a whole lot more over the land. So for the same amount, wow, this thing smells like it's burning. Yeah, I'm gonna put that away. So for the same amount of light, it's getting spread out more on a larger amount of land. So it's like you're taking more energy. No, you're taking the same amount of energy in the sunlight, but you're spreading it out over more stuff so that not everything heats up as much as if you took the same amount of energy and just concentrated it on one spot, right? So think about a hairdryer. If you take a hairdryer and you shine it right on your ear for a while, your ear is going to, I don't know, burst into flames, whatever, right? But if you take it and you go, everything dries, but it doesn't get all hot like your ear did when you just went, right? So you're taking like a same amount of energy, but you're spreading it over more of your area. So everything heats up, but it heats up less than if you just concentrated it all on one spot. That's what's happening in the wintertime, right? The sunlight is getting spread out over a bigger area. And so everybody heats up less. Now, when it's the summertime, we're on the other side. And now, yes, now we're getting hit a lot more directly with the sunlight because we're tilted right up towards the sun. Yes, we're further away, but the angle is right dead on. So we heat up a lot more. So one little fun thing about why we have seasons is because there's a tilt. The axis of Earth is tilted. And if it wasn't, we wouldn't have seasons. It'd be the same all the time, right? That would be kind of like if you lived on the equator. And on the equator, it's basically the same season all the time because the sun is pretty much, it doesn't go too far away from overhead all year round, right? So it basically does, right? This is why people go to live in places like the tropics, or where's Hawaii here? Hawaii, oh wow, Hawaii's way up there. No, Ecuador, that's a great place. It's on the equator. Places in Africa, Kenya, the equator goes right through Kenya. Singapore, right? All these places. So they don't really have winter. They don't have snow. They have sun and temperate climate all year round because the sun is always doing the same thing. Okay. All right. So I'm looking at the clock here and it looks like we got only 2 or 3 minutes left. So here's what I'm going to do. We're going to wrap up this stuff here. On Thursday, we're going to go over some more stuff about what we know about Earth. How did we figure out that Earth is a globe? How do we figure out about how big it is? How do we know about how big and how far away Moon is? What about Sun? We're going to go over some of those thinkings and some of those calculations. And we'll do a lot of drawings of that kind of thing. So I'll stop with this stuff for right now. How'd that go in general as a first day? Anything that I could be doing a little better? Because if there is, you know, I would love to know so I could make adjustments. If you don't want to tell me right now, that's fine. Send me an email, but I do look for feedback because ultimately you have to watch this. You have to watch this monstrosity. So I would love to know if things are going okay. So if you have any questions, if you have any comments, let me know. If not, fire me an email if you want to do that. I would like to leave you today with one last idea, which is that physics is all around you. And I hope that after this class is over, and even while it's going on, you'll be able to look around and you'll see things just slightly differently. You'll look at just something as easy as light coming through a window. And you go, oh wow, I know that light, that's not large enough to excite the electrons in the lower level. That's why it's transmitted by the glass. Ah, wow, right? I saw some rainbows the other day. I love rainbows. Yeah, it's the refraction through the droplets in the atmosphere. It's all great stuff. So I hope that you all have a different perspective on how you view things. That being said, I hope you have a great day. Happy first week. I'll see you back on Thursday. Good luck, folks.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.